In section 10.3, we'll be wrapping up everything that we know about the gas laws, and we'll really be bringing it home because we're talking about the combined gas law, we're moving on to the ideal gas law, and we're actually going to see how to convert from a certain volume of a gas and converting it to the number of moles of that gas. So now, this is what we've seen so far. We've seen Boyle's law, Charles's law, and Gay-Lussac's law. And I want you to notice that they're all very similar to each other, especially for Charles's and Gay-Lussac's laws. Notice that they're all being divided by temperature. The only difference here is whether you're taking volume or pressure, which one is being divided by the temperature. And what's interesting for Boyle's law, there's no dividing by the temperature on Boyle's law, but there is, the pressure from Gay-Lussac's law and the volume from Charles's law. And so actually we can take these math formulas, which are very similar to each other, and we can combine them into a single formula for this one. So this is where we get the combined gas law, where we have all three different parameters for our problems. We can account for the pressure, we can account for the volume, and we can account for the temperature using this formula. Notice that I have all three formulas in this single combined expression. Where I have pressure times volume, this comes from Boyle's law. I have pressure over temperature, this comes from my Gay-Lussac's law. And I also have volume over temperature, this comes from the Charles's law. And so this is a very useful way to do problems that are a little bit bigger and that we don't have to worry about all three variables are changing in a problem. We can actually handle all this. So now, what a combined gas law problem might look like is something like this. A sample of fluorine gas occupies 810 milliliters at -3 degrees Celsius and 1 atmosphere of pressure. What volume does the gas occupy when the pressure is doubled and the temperature increases to 127 degrees Celsius? And the trick from all these problems is knowing how to read the problem and getting information from that. So from reading that, the first sentence tells me that I have 1 atmosphere of pressure. So I can say that as my P1, 1 atmosphere, and I have 810 milliliters to go with that, and -3 degrees Celsius is my temperature. Remember that I can't use the Celsius temperature, it has to be converted into Kelvin. So just add 273 to your Celsius number, and my temperature for this one is 270 Kelvin. And so this is all my first set of information. All my P1, V1, and T1 are all paired together, and they will all go on the left side. So now if you keep reading through the problem, it asks the question, what volume? This will be the unknown, and it says that the pressure is doubled. So now if we had 1 atmosphere of pressure to begin with, if we double that, we get 2 atmospheres of pressure for our P2. Then the volume, again, this is what is unknown. This is what we want to answer in the question. And my new temperature is 127 degrees Celsius. And again, I can't use Celsius in these formulas. They have to be Kelvin. So add 273 to 127, and my new temperature becomes 400 Kelvin. And so now, I know it feels like there's a lot going on, but it's the same as the other problems that you've seen. It's just a matter of filling in what you know and solving for the unknown using algebra. The only difference here is that we have a lot more variables to work with, but again, out of all these, we know 5 of them, 1 of them is missing, so just multiply and divide for what you need. And so I won't waste your time on going through this problem together. Just know the answer is 600 milliliters. You can try it out to see if it's working out for you, and if not, let me know so we can troubleshoot that. Moving right along to ideal gases, we already talked about these back in the first section, but I just want to remind you of the assumptions that we've made about our gases so far. And it's that, again, our ideal gases have no attractive forces between them. They're not attracted or repelled by each other, so this makes it easier in our calculations, as well as our gases take up 0 space. We think of the particles as being single points that aren't really in 3D. And so now those are assumptions that we're making to simplify our formulas, but just know that in real life, gases aren't all ideal. The only time they can behave like ideal gases is when they're at a very high temperature. They're moving so quickly that they don't care what's nearby. They're not attracted to each other. And again, when we have very low pressure, when there's a lot of distance between our molecules. And again, we do all these just as an approximation to getting pretty darn close on our numbers for our formulas. All right, so now we can talk about the ideal gas law. And so it's using a lot of the things that we've talked about before, but it's adding in 2 new things. So we have a pressure of a gas, and we can measure its volume as well and its temperature. And again, this is all done in Kelvin. Now, what we're adding on here is the variable n, and this is for the number of moles. We can actually measure the moles of our gases as well. And R is the ideal gas constant, which is not something that we measure. It's called a constant. It will be the same in every problem, and it's just number that we use to adjust our results into actually usable numbers. And so now, I know that I told you that the ideal constant will always be the same, but there's actually a few different constants that we can have. Now, I should say that these are all worth the same, but all that matters is the unit of pressure that you're using. Because notice that all of these are set liters times a pressure over Kelvin times the mole. And so what's changing on here is the unit of pressure. And the most common one we'll be seeing is this one in the center, 0.0821, because this measures my pressure in atmospheres. But just know that if you get a problem thrown your way and it asks for the pressure in kilopascals, then you would use this number, 8.3145. Or if the pressure is in millimeters of mercury, then the number is 62.4. Just know that these are all worth the same, and they only look different because you're using different pressures. So let's see how to solve a problem with the ideal gas law. So a question might look like something, how many moles of nitrogen are present in a 2.0 liter container at 27 degrees Celsius and 1 atmosphere of pressure? So again, as long as you can read this problem and draw information from it, then you know what to plug into your formulas. So these are the things we can draw from the problem. We know that my atmosphere is 1 atmosphere of pressure. We know that the volume is 2.0 liters, and the temperature is 27 degrees Celsius, but we can't use Celsius. It has to be in Kelvin, so we add 273 for our 300 Kelvin temperature. And finally, R will be using 0.0821 because our pressure is given in atmospheres, so we use the atmosphere constant. All right, so now all that's left to do is that we have our formula, we plug in what we know and solve for the unknown. So when you do that, here's my formula. PV is equal to nRT. My pressure is 1 atmosphere multiplied by the volume of 2.0 liters, and we set that equal to 0.0821. This is the gas law constant times 300 Kelvin times our variable n. The results that you get on the left is 2.0. The result on the right is 24.63 n. So now if you divide both sides by 24.63, you get the result of 0.08, and this is the number of moles in our problem. So all these problems just comes down to a little bit of algebra once you're able to set up all your different variables and knowing what each of them are. The last thing to talk about is Avogadro's law, because we can use this to convert between the number of moles, the amount of gases that we have, and their volume. And so if this name sounds familiar to you, Avogadro, it should, because we used Avogadro's number back in our unit when we were converting between number of moles and its number of particles. And the funny thing about Avogadro's number is that Avogadro never actually knew this number. His work dealt entirely with gases. He never tried to count the number of molecules in something, but this number was assigned and named after Avogadro in his honor after it was proven right years later. And so now, Avogadro's number dealt with Avogadro's work dealt with gases, and he hypothesized that the same volume of gases, no matter what they were, always had the same number of molecules. It was made of the same amount of stuff. And so the way that we can say this is that the number of moles in a specific volume of an ideal gas will always take up the same size no matter how big the molecules are, how much they weigh, or what they are. Now, in practical terms for us, is we just need to know that a mole of any gas will always take up 22.4 liters of volume when it is at standard temperature and pressure. And we'll be using that number, that 1 mole is equal to 22.4 liters. We can use it as a conversion factor in our problems. All right, so for practice, let's look at these two conversions. Now, what volume will 4.6 moles of CO2 gas occupy at STP. So what we need to know from this is that we have 4.6 moles of carbon dioxide gas. We can set up a conversion table around that, and we're trying to change our number of moles into liters. And remember that our conversion factor is 1 mole of a gas is 22.4 liters. If you do this calculation, 4.6 times 22.4 liters divided by 1, you get the result of 103.04 liters. So now let's change up the gas. We still have the same amount of moles, 4.6 moles, but now it's nitrogen gas, N2. And actually, the problem ends up being the same because it doesn't matter what gas we're looking at, as long as it is a gas at standard temperature and pressure, it will always take up the same amount of room, 22.4 liters. In this case, if we have 4.6 moles of any gas, its volume is 103.04 liters. And we can use this idea to answer more complicated questions, or questions that seem more complicated, but it's just goes back to our stoichiometry unit. Now, a problem might be something like, given the combustion reaction of C3H8 plus 5O2 yields 3 CO2 plus 4 H2O, how many liters of carbon dioxide can be produced from 1 liter of O2 at standard temperature and pressure? And so it's just like the problems that we did when we're dealing with mass of a certain compound. We're only using liters instead, knowing that we are at standard temperature and pressure. So we start with 1 liter of our oxygen gas, and we want to convert this into the number of moles, because again, we can't compare liters and grams using a chemical equation. We need to compare moles. So we're going to take this 1.0 liters of oxygen gas and convert it into its number of moles. So use the conversion factor of 1 mole is equal to 22.4 liters. Up here, I'm starting with liters, so I want to set liters on the bottom in my next section. So I have to set 22.4 liters of O2 is equivalent to 1 mole of O2. All right. Turn this into a calculation where we have 1.0 times 1 mole of O2 divided by 22.4. Remember that the liters of O2 cancel on this one because they're matching top to bottom. Do that calculation, and you should get the result of 0.045 moles of O2. Now that we know the number of moles of oxygen gas, we can relate it to the chemical equation to know how much carbon dioxide we can possibly make. So now take that result that you just got, 0.045 moles of oxygen gas, and set up a mole factor mole ratio to convert from moles of O2. Here I have 5 moles of O2 will change to 3 moles of CO2 according to my balanced chemical equation. All right, so turn that into the calculation, so where we get 0.045 times 3 moles of CO2 divided by 5. If you put that through your calculator, you should get the result of 0.027 moles of CO2. All right, so now we know how much CO2 we produce, but we know this number of moles. The question is, how many liters of it can it be? All right, so now there's just one last step to go through. We will take that same result that we just got, 0.027 moles of O2, and set up one last conversion, again using the Avogadro's law, where 1 mole of any gas, doesn't matter what it is, and this time it's CO2, will move to 22.4 liters of that gas. So if you make this calculation, 0.027 times 22.4 liters of CO2 divided by 1, put it through the calculator, and you should get the result of 0.6 liters of CO2. So these are, in my opinion, the most difficult looking problems, but they're not actually that difficult if you know that all you have to do is set up 3 conversions to go from it. Or sometimes it might be 3, sometimes it might be 2. It's just a matter of knowing what units you need to hit and what units you need to change out of. All right, so that's going to do it for our unit on the gas loss. Now there's only practice problems to run through. Make sure that you understand how to do these and that they won't be bothering you anymore.